Managing large amounts of data can be challenging, especially when you also have to manage the storage system where the data lives. So, to make life easier for storage administrators, NetApp offers a data ops toolkit that can offload some of the work associated with storage management. On this Tech ONTAP Podcast episode, we welcome the creator of the toolkit, Michael Oglesby, to talk about the latest updates and where best to use it.
Welcome to the Tech ONTAP Podcast.
I love NetApp.
Oh, yeah.
I love NetApp because it's so fun.
I'm here in my studio, of course, in the basement, as you can see, well-lit basement. I'm here with Mike Oglesby, who's actually in the office because, we thrive in the office. So, Mike, what do you do here at NetApp and how do we reach you?
Yeah, I'm here in the RTP office with a blank white wall behind me in a conference room. But yeah, I'm Mike Oglesby. I'm a software engineer here at NetApp focused on AI solutions specifically. So this would be essentially anything outside of the core product that involves using our products for AI use cases. So reference architectures, tooling, integrations, develop code, write technical reports, solution documentation, all that good stuff. And you can reach me either by email, moglesby@netapp.com, or LinkedIn is the best social media to find me on. I don't really do much on other social medias.
Yeah, I don't think many people do anymore.
Yeah.
It's mostly all LinkedIn, which is kind of funny because, 5-10 years ago, nobody would have been like, oh yeah, find me on LinkedIn. But now,
Yeah, I can't even remember the last time I opened Facebook. I occasionally open Twitter or X and then quickly regret it.
Yeah, it's definitely become kind of a cesspool.
Yeah.
But hey, it is what it is. So you mentioned that you work on AI workflows, you work on AI use cases, and one of those includes the large language model. So I know that's a hot topic these days with generative AI and all the other AI things floating around out there. Tell me a little more about large language models, what they are, and some of the general workflows.
Yeah, so LLMs are the 800-pound gorilla in the AI space these days. A lot of people, when they say AI, they basically mean LLMs. That's what they're talking about. They mean Gen AI with LLMs. It's kind of become almost synonymous with the term AI. It's been the hot topic ever since ChatGPT came out. But for anybody who's not familiar with terminology, I'm sure you're familiar with ChatGPT and Gemini and Claude. And basically, those are chatbots that are powered by LLMs. A large language model is the type of AI model that sits behind those chatbots. You submit a prompt, it's fed through this LLM. The LLM responds to your prompt, and the chatbot prints the prompt out to you. So the LLMs are the brains of all these chatbots that are out there.
Yeah, it's kind of the librarian, right? So you've got this big old catalog of books and information and knowledge out there. And the LLM's job is to find a specific section of the specific book that you're asking about. And it's really only as good as your prompts. So you have to be really specific.
Yeah, technically speaking, what it actually does is look at all the previous words in a sequence and predict the next word, essentially. The prompt is divided into tokens, and then it predicts the next token. A token might not match one-to-one to a word, but you can think about it as you submit a prompt, a sequence of words, and then one by one, it predicts each of the next words based on all the content it was trained on, which for most of the LLMs out there is essentially the entirety of the public internet, plus a bunch of public domain books, plus a bunch of books that were picked up at a used bookstore by an Anthropic employee, stuff like that.
Yeah, and like any database or data store, it's only as good as the information it's fed. So that becomes a really big part of it when you're trying to build a large language model that does what it's supposed to do.
Yeah. So that's a good segue to deploying LLMs in an enterprise setting. These LLM were trained on like general public stuff, right? So the public internet, books, just anything that the researchers could get their hands on that was the corpus of text that they used for training. But that doesn't include your private data within an enterprise. And so since ChatGPT was released, basically every enterprise everywhere has been scrambling to figure out how to apply LLMs within their enterprise and augment them with their private data. And really, there's three primary ways you can do this. For unstructured data, meaning just like LLMs work on text. So when I say unstructured data, I mean unstructured text. Basically, you can either fine-tune the model. So you can take a foundation model. Typically, you would use an open source model if you were fine-tuning like one of Meta's Llama models or one of the Mistral models or one of the DeepSeek or Qwen models. And you would essentially modify the last few layers of it by training it on your private data. That's kind of hard. You need a certain amount of GPU horsepower, and you need some AI researcher skills to be able to do that effectively. There's frameworks you can use to help you, but it's still not a small undertaking. And then you have the headache of keeping it up to date. As your source data changes, you have to refine tune your model periodically to keep it up to date with your source data. So what most enterprises, private organizations are doing is implementing RAG, or retrieval augmented generation. Basically, this was the hot topic a year or two ago, and there were POCs running everywhere. And now these types of deployments are actually starting to go into production. I know we have a pretty extensive RAG deployment running in production here at NetApp, serving internal NetApp employees. But basically, you take a corpus of source data. So this could be your private code bases, your private wiki pages, your private knowledge base entries, any unstructured text, and you vectorize it. Essentially, you run it through what's called an embedding model to generate vector representations of the text, which you store in a vector database. And then anytime a prompt comes into the LLM, you can take that prompt, vectorize it, perform a similarity search on the vector database, return any similar vectors, and essentially append them to the end of your prompt or augment your prompt with these similar vectors. Hence the name retrieval augmented generation. You retrieve them from the vector database and then augment your prompt. And it takes some DevOps skills, some platform engineering skills to deploy something like this. You typically have to code up a simple pipeline to keep the vector embeddings up to date, stitch a few tools together, but it's not as daunting as fine-tuning a model and continually keeping that up to date. You can use standard off-the-shelf tools, open source tools like VLLM, or proprietary tools like NVIDIA's suite of NIMs to deploy these LLMs with off-the-shelf configs. It's much more approachable. So this is what most enterprises are doing. But then there's a third way to augment LLMs with private data, and that one applies more to structured data. So I've been talking about unstructured data when I talk about fine-tuning and RAG, unstructured text specifically. But let's say you've got a bunch of databases with relevant data in them. You've got maybe a data lakehouse with tables in it. You've got Salesforce data sitting behind an API. You've got all this structured data or even semi-structured data that you want an LLM to be able to access. Well, how do you give it access to that? And this is where Agentic AI has a solution in terms of this new emerging agentic tool use model. So this new model where you have AI agents, which are essentially LLMs with a wrapper that have a set of tools available to them. And so basically you could have a text to SQL and a SQL query tool that you present to an AI agent. So you could have an AI agent that takes a prompt, calls its text to SQL tool, or uses the LLM itself to generate a SQL query from the prompt, and then calls its query tool to go query your database, gets the data back from the database, the results, of the query and then feeds those in with the prompts to the LLM, and then the LLM can submit out a response. So there's this third agentic tool use model that's becoming the standard for augmenting LLMs with private structured data. And these two things are kind of merging together as everybody moves more towards this agentic AI model. Now you have one AI agent, so a LLM with some orchestration coding around it that tells it what tools it has access to, what its role is, what it can do. That kind of bounds the prompt. And then it might have access to a SQL query tool, so it can query structured data. It might have access to a Salesforce API call tool. It can go call the Salesforce API. It might have access to an SAP API tool. It can go talk to SAP. And then it also has access to a vector database where it can perform a similarity search. So that's RAG, but now RAG is presented to the AI agent as just one tool and an arsenal of tools that the agent has access to. So when you hear about agentic AI, it's LLMs with an orchestration wrapper that have access to a set of tools, and those tools could be tools that give it access to private.
Would you say that agentic AI can be run basically on a per workstation basis, whereas something like a RAG would run on a set of servers that people access individually?
It could be, but it depends on what you're doing. There's still often a need to use bigger LLMs that basically need a bunch of GPUs to run on. Oftentimes, these agentic AI systems are following the model of a client application where basically like the scaffolding, the orchestration code sits, and then it talks to an LLM via an API, essentially crafts a prompt, feeds it into the LLM. The LLM comes back and says, hey, okay, here, call this tool, and here's the parameters to pass. And so the orchestration could sit on a laptop. It could also be sitting in a platform like Salesforce or in Microsoft Copilot Studio. Agentic AI is a very broad term, but oftentimes the LLM itself, depending on how big of a model you need to run, how much smarts you need, in quotes, LLM itself is often sitting behind an API. So that could be a VLLM instance that you host on, say, a NetApp AI pod, or it could be a NIM that you host on a NetApp AI pod, or it could be like the Azure OpenAI service. Industry has standardized on the OpenAI API spec. And so all of these tools and API services I just mentioned actually serve the same API. And so that makes them somewhat interchangeable in terms of being able to plug them into tools. Obviously, there's models that are exclusive to certain providers and that sort of. But that's the most typical setup is the client agentic AI app might be on a laptop, might be on a general purpose server or computing environment, and it's talking to an LLM that's hosted somewhere else via an API.
So I guess there's a standard, but not a standard at this time, right? It's kind of a moving target at this point.
Yeah, it depends on the use case, really. If you just want to do some simple tasks on your laptop, you've got a MacBook Pro or something like that, you could deploy an 8 billion parameter model on your MacBook Pro, and it's going to be plenty good for searching your file system or editing some text files or small things like that. But if you're trying to really do something sophisticated, you're going to need a bigger model, and you're going to run out of horsepower on the edge device.
Right. And that's when you basically come into servers or storage solutions like a NetApp.
Yeah, so that's where you could subscribe to an API and pay per token. You could subscribe to OpenAI, the Azure OpenAI service, or the Vertex AI API service, the Gemini API, and pay per token, or you could self-host. If you were seeing heavy usage and you wanted to optimize, buy some GPUs, you buy the NetApp AI pod reference architecture, either the NetApp AI pod for DGX, where we have a validated, certified reference architecture that pairs NetApp AFF systems with NVIDIA DGX servers or the NetApp AI pod with Lenovo, which is not quite as powerful as the DGX. It's L40S GPUs as opposed to the cutting edge B200 GPUs. So you could buy one of these, you could deploy a NVIDIA NIM on it to host an open source LLM, and then you've got your AI you can talk to.
And really, it just comes down to how much do you need? What do you want to spend? How important is it? And all those questions, I guess, are kind of hard to answer sometimes.
Yeah. And honestly, beauty of our storage platforms here at NetApp is they work with open protocols, right? And we have services in each of the major clouds, and we have the ability to seamlessly and efficiently move data across different environments. So we can work with you either way. If you don't want to buy and host your own GPUs, or you don't have the power in your data center to do that, or maybe you don't even have a data center, you can still hook your NetApp storage either on-prem or in the cloud up to your AI application and use one of these cloud APIs or subscribe to an API service for your LLM. So the beauty of NetApp is you have options.
Yeah. You're not just buying hardware. You can definitely leverage rental type of scenarios with as a service models type of things.
Exactly.
So I know that you work specifically on the Data Ops Toolkit for NetApp, and I'd like you to tell me a little bit about what that is, if it incorporates some of the stuff that you're talking about, and if it doesn't, what else it does.
Yeah, so this is a good time to revisit the Data Ops Toolkit because there's some new stuff we're developing that's very relevant to this new agentic AI model. So quick refresher, the Data Ops Toolkit is a Python module. It's open source. The code's on GitHub, and then we also package it and push it to the PyPy repo. So you can install it with pip. There's two different packages, one package for Kubernetes and one package for basically any other environment. So you run pip install NetApp Data Ops traditional or pip install NetApp Data Ops -K8s. And basically what you get when you install it is a library with a set of simple functions that you could import into a Jupyter notebook. If you're a data scientist that wants to, let's say, on demand, take a snapshot of your training data set for traceability purposes or just for backup purposes. Or let's say you're a platform engineer putting together some automation, you could import these functions into an automation script that you're developing in Python. These are just super simple Python functions that make it easy to consume some of our key capabilities in ONTAP. So I mentioned creating a snapshot. There's a create snapshot function. There's a create volume function. So you could have an automation script that anytime a data scientist requests a workspace, it goes and creates a volume and mounts it on some sort of client machine and gives the data scientist access to the workspace. There's also a simple function for cloning a volume. So let's say you have a massive data set and you're using it to train or fine-tune an AI model. You can call this function to near instantaneously using our Flex Clone technology, clone that data set. So let's say you've got a gold source data set and then you're running a bunch of different experiments. You can clone it on demand, run your experiment. Your gold source is still preserved. You could have 5 different people cloning it and running 5 different experiments. In the Kubernetes flavor of the toolkit, there's also, because it has access to Kubernetes scheduler, it has the ability to provision apps essentially on top of the volumes. And so it has all these same create volume, clone volume, create snapshot capabilities, but the objects it creates are Kubernetes native objects. So if you're familiar with Kubernetes, when you create a volume, it creates a persistent volume object and a persistent volume claim object on your Kubernetes cluster. It uses Trident, our CSI driver under the hood. And so it has all the same create volume, clone volume, create snapshot capabilities, but it also has the ability to create Jupyter Lab workspaces, which are basically, it's a web interface where data scientists and data engineers can work with Jupyter notebooks interactively. And so with one function call or one command, create a Jupyter Lab workspace that's backed by a NetApp volume. So a data scientist could say, create me a 500 terabyte Jupyter Lab workspace. A few seconds, they get a URL they can drop into their browser. They can pull all their data into this workspace. And it looks to them like they're working with any other Jupyter Lab workspace, but it's all backed by NetApp. So anything they pull in is saved on a Trident persistent volume, and then they can clone the workspace on demand, can snapshot the workspace for backup or traceability. So because it has access to the Kubernetes scheduler, it can provision apps like Jupyter Lab on top of the storage. I've been talking about functions. We also package a simple CLI with the Toolkit. So in addition to a create volume function, you can import into any Python program or block of code. There's a CLI. And if you're in a terminal, you can run NetApp DataOps CLI create volume. And it's a quick and simple way to create a volume. So that's what the DataOps Toolkit is. We originally created it as a simple way for like the data scientists, data engineers, ML platform engineers of the world to take advantage of our capabilities without having to learn the ins and outs of ONTAP.
Right.
The storage admins can carve them out an SVM or a sandbox for them to do their work in, and then give them the credentials to it, and they can set up their credentials file for the DataOps Toolkit and then do whatever they want within that sandbox. So that was the original conception of the DataOps Toolkit and how it's being used today. Where it becomes relevant to this world of Agentic AI is, I've talked about how Agentic AI follows this model where you have AI agents that have access to a set of tools, right? So the DataOps Toolkit has these very simple wrapper functions for administering volumes or snapshots that lend themselves to being tools that an AI agent can consume. And so we are now working on building an MCP server into the DataOps Toolkit that's now going to let an AI agent call these functions. So this AI agent could be as simple as GitHub Copilot Chat. So GitHub Copilot Chat supports the MCP protocol. So you could add this MCP server to your GitHub Copilot Chat running in your VS Code on your laptop, and you could type in the chat, create a new volume for me on my NetApp system and mount it on my server. And it'll go see that it has this create volume tool available to it from the DataOps Toolkit. It'll invoke it. That'll go create a volume on ONTAP and then mount it locally on the machine the user's working on. And likewise, you could say, okay, I have this volume I'm working with where I have a data set. Clone this volume for me. I want to clone my volume. And it would just go off and call that tool and clone the volume. You could say, hey, I'm at a stopping point. Create a snapshot of my volume for me for traceability. And it would go do that for you. If you had access to a Kubernetes cluster and you had your kubeconfig file on your laptop, you could say, hey, go create me a Jupyter Lab workspace. It goes and invokes that create Jupyter Lab tool, and LLM will come back and say, okay, I created it for you. Here's your URL. You can put into your browser to access your workspace. So essentially, it's the same functions now presented as tools to an AI agent that can be prompted in natural language. So the Hub Copilot Chat is the simple use case. The Copilot Studio, chatting with that, setting up a simple chat bot chat in front of that is another simple use case. But it could be as sophisticated as you could set up some autonomous AI agents. You know, maybe you're using something like Salesforce and a ticket comes in, and then the AI agent looks at the ticket, figures out, I need to create a volume to fulfill this ticket. It has access to that MCP server. It just automatically goes and creates a volume, and then it goes and fulfills the ticket without anybody ever having to take a look at it. And so you could get as sophisticated as these autonomous AI agents that are working in an environment and responding to different requests that come in or different events that happen. And now they have access to some volume and snapshot administration tools. This is how we're evolving the DataOps toolkit to now make it relevant to this new world of AI agents. And I can go ahead and circle back to MCP since I mentioned this is going to take the form of an MCP server. So what is MCP? MCP is the Model Context Protocol, and it was originally created by Anthropic. Seems like a lifetime ago, but it was earlier this year. It's taken the world by storm. Everybody's building an MCP server now. And it's a common framework for defining tools and exposing them to AI agents. So there's a bunch of client applications out there, Agentic AI tools that support MCP. So I mentioned GitHub Copilot Chat, Copilot Studio. There's agent SDK frameworks like NVIDIA Agent IQ, LangGraph, and others that support MCP. Claude Desktop is another application. Anything LLM, there's a ton of them. And so it's really been quickly adopted by the ecosystem as a standard way to present a set of tools defined in code to AI agent.
So I know the DataOps toolkit is intended for AI use cases. Could it extend out into other use cases like version control, source control type of stuff?
Absolutely, yeah. And we actually have a couple customers using it for those types of use cases. We intentionally called it the DataOps toolkit and not the MLOps toolkit or AIOps toolkit because we knew there would probably be some applicability outside of AI use cases. These AI use cases were the inspiration for it. But we've got a customer in the semiconductor space, actually, that's using it to manage dev workspaces and build workspaces. And then we have a customer in the public sector space that's using it to manage dev workspaces and that kind of thing. We'll see more of that because this MCP server that we're developing can expose some of these capabilities to really any type of AI agent.
Yeah, actually, I talked to a customer today that this probably would fit. So I'll point them your way.
Yeah, sounds good. Yeah, and in the initial release of this MCP server, the only tools available will be these simple volume snapshot clone type functions that are available in the DataOps toolkit today. But we do plan to build out more tools, and we're actively soliciting feedback from customers on tools they'd like to see. So would love to have a conversation with them.
Yeah, absolutely.
And anybody, feel free to reach out. Let me know what tools you'd like to see.
Are you leveraging consistency groups at all, where you can consolidate snapshots across multiple volumes?
No, we're not doing that now, but that's a good idea for another tool to add. Yeah.
There you go. Yeah. So I know that one of the challenges to these workloads is performance, and some of that performance is out of your control because it's basically your infrastructure. Some of it is in your control, and there's ways to get around some of those issues through things like caching and that sort of thing. Tell me a little bit about the work you've done in that area.
Yeah, so optimizing LLM inference performance is a hot topic these days because nobody can get their hands on enough GPUs. And so everybody's trying to make sure they're fully utilizing and optimizing the GPUs that they have. And so you want to make sure you're optimizing your workloads so that you can use as few GPUs as possible to host them. So what that means for LLM inference is there's things you can do. VLLM has become very popular as an inference framework because of its performance. It's very performant. And then there's also parameters you can tune, like the batch size and the max sequence length, depending on your use case, to optimize utilization. But then another topic that's become very popular recently is KV cache offloading. Basically, when an LLM is performing inference, so when it's processing a prompt, for each new token that comes in, it has to calculate what's called an attention value. And we could probably spend a whole hour talking about what attention is and all the different parts of an LLM. But the important thing to know is just for every new token, there's an attention value that needs to be calculated. And to calculate that attention value, you need all the previous attention values from all the previous tokens in the sequence. So let's say you submit a long prompt, and then the LLM spits out a long response to, for each additional token in your prompt as it's processing your prompt, it has to take the previous attention values into account. And then when it starts generating its response, there's an attention value for each new token. And so recalculating all these attention values that have already been calculated, that would be a lot of wasted compute resources. So you want to store these somewhere, right? So you can reuse them for each new token in the sequence. And so the concept that has become the standard is something called a KV cache. What folks have been doing is basically carving out a section of GPU memory for a key value cache. And essentially, it's as simple as it sounds. It's a bunch of values with keys associated with them. And so all those previous attention values are stored in this KV cache in GPU memory. And for each new token that comes in, they're quickly retrieved so that the new attention value can be calculated. But there's a massive drawback here, and that's that GPU memory is limited. So you are sacrificing some of your GPU memory and using it to store this KV cache in order to save on compute intensity. So it's of a trade-off between GPU memory and compute intensity. GPU memory is important because when you perform inference on an LLM, the entire model has to be loaded into memory. And these models can get pretty big. If we're talking a 70 billion parameter model, you often need to host that across like 4 GPUs to fit it in VRAM, maybe even more depending on how you tune your parameters. The more of your memory dedicate to KV cache, then that's less memory you can use to host your model. If you were hosting a model without a KV cache, maybe you use 2 GPUs. We're talking about a small model. When you introduce a KV cache, you might now need 4 GPUs between compute intensity and GPU memory utilization. And so using the KV cache might make the LLM run faster, and you need it to make the performance acceptable, but it causes you to need more GPUs. And so there's been an interest in being able to shrink the amount of GPU memory or VRAM that's used for the KV cache and essentially offload the KV cache or a portion of it to an off GPU target. So that could be CPU memory. That's something that some folks are doing, but it could also be really fast external storage. That's also something that a lot of folks are interested in doing or have already implemented. And so I mentioned VLLM, which has emerged as a popular inference framework because of its performance characteristics. There's a project called LM Cache, which you can think of as a plugin for VLLM. And they have become the standard for essentially adding KV cache offloading to VLLM. There's a bunch of different offload targets that they support. The two most interesting, in my opinion, are CPU memory and a GDS backend. GDS stands for GPU Direct Storage. That's NVIDIA's framework for allowing a GPU to talk directly to external storage, bypassing the CPU. It uses RDMA. They support some other external storage targets, but this one's particularly interesting because when you use GPU direct storage with really fast external storage, there's not that much latency. What's interesting for us here at NetApp is it supports any GPU direct storage file system that's mounted on the client. And at NetApp, we support GPU direct storage over NFS without any proprietary client, any sort of proprietary file system client or drop-in replacement NFS client. You can use Linux. You can use the standard NFS client. Just set the appropriate mount options. enable the right settings on your ONTAP box, and you can use GPU direct storage to talk to an ONTAP system over an NFS mount. And so what this means is with VLLM and LM cache, we can support KV cache offloading using industry standard tools and protocols, no weird one-off proprietary or potentially unstable file system clients, just industry standard tooling on both the inference and storage side, and it just works. And so this is something we recently validated and that I wrote up a blog on. So you can find that on the Tech ONTAP community blog site. It just walks through how to implement KV cache offloading to ONTAP using GDS with VLLM and LM cache. It's pretty easy. You just sit.
Sounds pretty easy.
Yeah, that's the cool thing about it. And it just works.
Would the KV cache be something that's worth snapshotting, or is that so ephemeral that it doesn't really matter?
Yeah, it's a good question. And that's something I've thought about. I have not seen use case come up yet, but I could see it being worthwhile, especially in a world of AI agents that have ongoing conversations with an LLM, basically, where the context can get pretty long, but it's all part of the same conversation. At least snapshotting it for DR purposes could probably be useful. If something goes down, you could fail over to a different region, bring the whole environment back up, and the KV cache is already there. Maybe if something gets funky, you can restore your whole environment. You could even have something like Trident Protect running in your Kubernetes cluster, backing up your VLLM instance. And if something gets wonky, you just restore the snapshot for the volume that the KV cache is being offloaded to, and it just picks it right back up where it left off. And a new API request comes in, that KV cache is already there.
What about something like a flex cache that hangs off of that volume that can localize those KV caches to cloud instances?
Yeah, that could also be interesting as we get into distributed inference environments where perhaps there's different GPU farms all serving the same API endpoint or something like that, where you want to share that KV cache so that you can route requests to wherever you have GPUs available. I haven't seen this stuff being used in real life yet, but I think there's a bunch of different interesting things you could do, and I think we're kind of just scratching the surface here. So I look forward to seeing all this stuff get built out as our customers move further down this path.
Is there any advantage to leveraging block devices for this, or is it just kind of like you want to have a shared storage like NFS?
You really want to have a shared storage because when you have a multi-node deployment, you want that same KV, especially if you're splitting one model across multiple nodes. You want that same KV cache to be available on both nodes. And that's one of the benefits of offloading to external storage versus CPU memory, is you can share that KV cache across nodes. And so you don't have to unnecessarily recalculate attention values that have already been calculated on a different node.
Okay, makes sense. You can share all the values across all the clients.
Yeah.
With Flex Clone, you could also spread that workload across multiple CPUs in your cluster, right? So if your volume is a flex vol and it's on a single node, and that's where your KV cache is, you could have KV cache copies across all the nodes, and that way you have redundancy, you have better performance potentially.
Yeah, for the validation, we used Flex Group with PNFS over RDMA.
Right.
And so to make sure we were fully optimizing performance on the ONTAP side. If you're familiar with the AI pod for DGX reference architecture, we use the mount options that are recommended in the best practices section of that reference architecture. You have to use RDMA to use GS. So that is one drawback. You have to have an environment that supports Rocky, RDMA over converged. If you don't have that, you can't use the GDS backend in LM. There's probably other ways you could implement the offloading. Performance probably won't be quite as good because the GPU is not going to talk directly to the storage.
How big do these caches get?
So they can get pretty massive when we're talking about a consumer service like ChatGPT. There aren't a lot of hard numbers coming out of those guys, but they're maintaining a lot of simultaneous conversations. I know I go into ChatGPT and I keep asking things in the same thread, and then I might go away and then I come back to it and I ask a follow-up. And so with those big consumer-oriented deployments, they can get pretty massive. If you have a long context and you're including a large amount of source material in your prompts to the LLM, then they can get fairly big there too, but we're still probably talking about a different scale than a Chat GPT. The tricky thing is we haven't really seen how big they can get because we've been bound by GPU memory. And so what folks have been doing is just throwing out old stuff and then they have to recalculate. So as we get into optimizing things further and offloading KV caches in production, I think we'll see these things probably grow quite large.
So is a KV cache associated with a single token or multiple tokens? Is it like a one-to-one or?
An attention value is associated with a single.
Okay.
But the KV cache contains all the previous attention.
Okay. So it's not
for all the previous tokens.
Is it per session? Like, let's say I open up a Chat GPT session. Do I get a KV cache with that? And then someone else opens up a Chat GPT session somewhere else. Is that an additional KV cache, or are they sharing that same cache?
So there is some sharing that goes on, but for the most part, because each attention value is calculated with all the previous attention values, your attention values typically aren't useful in someone else's conversation unless they ask the exact same, have the exact same conversation. So while they all might be stored in the same KV cache, what's going to be useful in processing your stream is all previous attention values from your stream that are in.
Okay. So the DataOps Toolkit incorporates KV cache offloading, I assume, with all the pieces like the NFS over RDMA and all that stuff, right?
You could use the DataOps Toolkit to provision the volume that you want to offload your KV cache to. And you could also use it to mount that volume if you wanted to. It can take custom mount options. And you could use it to clone that volume if you wanted to clone it to set up another deployment somewhere. But what someone would typically do is deploy their VLLM using Helm and just specify a specific PVC that they want mounted to it, and then specify all the right parameters in their config file to offload the KV cache to that PVC. And then PVC is going to remain, at least for that specific deployment, fairly static for the life of the VLLM.
Gotcha.
Yeah.
So it sounds like when you, say, start up a ChatGPT instance, it spins up a Kubernetes pod that creates a persistent volume claim, that creates a volume and uses the KV cache, and then it goes on its merry way. Is that kind of the workflow there?
Yeah. If they were using VLLM, that's how it would work. There's not a lot of details out there on how ChatGPT itself works. But yeah, your typical enterprise deployment is going to have either VLLM or NIM deployed in a Kubernetes cluster. If it's a multi-user deployment where usage really scales up and down, they've probably got a horizontal pod autoscaler that'll scale it out as more users are hitting it. And then essentially, there would be a volume that's mounted in each of those pods, and it would part of the pod spec where the KV cache would be offloaded to. And each new pod that comes up would have access to the existing KV cache.
Then when they're done, it tears it down and then deletes the volume, and they just keep going.
Yeah, if you tore down the whole deployment, but typically it would scale down to some small amount of pods, right? Like maybe one volume still there.
Gotcha.
Typically these things don't go away. They just scale up and down based on usage.
All right. Sounds like a lot of information there. I don't know that I've absorbed it all. Luckily, we'll have a transcript. You can go in and we could probably feed it into an LLM, and then it can make it nice and pretty and all that good stuff.
The LLM could probably explain it better and more concisely than. Yeah.
We're going to do that. We're going to feed it into an LLM. Say, hey, dumb this down for me, right? So if I wanted to find the Data Ops Toolkit or the blog, where's the best place? To the Tech ONTAP community, right?
Yeah, so the Tech ONTAP community is where you can find our LLM inference blog series, which is an ongoing series. Got some recent posts on how to deploy VLLM on Kubernetes with a chatbot front end, and then how to add KV cache offloading to ONTAP with GDS, how to add that to that deployment. So that's out there on the Tech ONTAP community site. And then the Data Ops Toolkit, if you just Google NetApp Data Ops Toolkit, GitHub repo should be your first result.
Okay.
So just go out to our GitHub repo. The first thing you'll see is the README, and that has all the information you'll need to install it and start using it. If you already have an ONTAP system or one of our cloud services, then you could go install it and use it. It's open source. It's free.
Yeah. Excellent. And the support for it, is that kind of like ad hoc? Like, how does that work?
It's community support via Git. So if you have an issue, just submit it to us on GitHub. We monitor it every day. We'll get back to you.
Okay, excellent. And are you on the NetApp Discord as well, or are you not?
I am on the NetApp Discord. Yeah, I primarily hang out in the artificial intelligence channel on there. So if you go there, you'll see some posts from me there, and feel free to reach out on there. And as we continue to post blogs in this LLM inference blog series, I typically drop a link in there as well.
And I assume we'll see you at Insight.
We'll see.
You see? We shall.
I assume so.
We haven't decided who's going,
Yeah.
but
Yeah.
I assume that both of us will be there.
Yeah, I assume so.
All right, excellent. Well, Mike, again, thank you for coming by and talking to us and being on video and all that good stuff. And if you want to check out the Data Ops Toolkit, feel free to do that. And, of course, TechOnTapPodcast.com. Yeah, that's all I got. So thanks again, Mike.
Yeah, enjoyed it.
All right, that music tells me it's time to go. If you'd like to get in touch with us, send us an email to podcast@netapp.com or send us a tweet @netapp. As always, if you'd like to subscribe, find us on iTunes, Spotify, Google Play, iHeartRadio, SoundCloud, Stitcher, or via TechOnTapPodcast.com. If you like the show today, leave us a review. On behalf of the entire Tech ONTAP podcast team, I'd like to thank Mike Oglesby for joining me today. As always, thanks for listening.
Oh, yeah. Is it just me that's getting off on this? Oh, yeah.